Uh, we are me, Dan LaRouche, Javan Watson, Rodolfo Nunez, and Smit Shah. We're going to start with an introduction, which is an overview of what fog computing is all about. And fog computing is a paradigm that extends the cloud to the edge via intermediate servers. And the idea of using the intermediate servers is to overcome some of the problems that cloud computing has introduced now that we have an explosion of end devices or edge devices due to the Internet of Things. And we'll get into some of the details and you'll understand it better as you see it. Now, fog computing's very new. It was first proposed by Cisco in 2012. And there's been a lot of research since then. And we're seeing that even as recently as last year, standards were first adopted by IEEE. And here we have even a more detailed timeline, which I'm not going to go through in great detail. The major new thing that you'll see here is that actually there was some research into the concept of fog computing in 2009, and it wasn't until 2012 that Cisco formalized it and adopted the name. And here we see a diagram of what a fog model might look like. But let's take a step back and think about cloud computing, the model that was prevalent before fog computing. And that would be this diagram without the fog platforms. And you would have the end users, which are PCs, Internet of Things, servers, whatever, all connected directly to the cloud, not going through the fog. And the problem that was emerging was, or problems that were emerging, I should say, were several. The bandwidth to the cloud servers became saturated. The demand with so many devices was horrendous. The cloud servers themselves became saturated. One server or a farm of servers having to service huge numbers of edge devices. And the latency. Many of these devices were sensors or controllers, and the sensor needed to pick up information and quickly alert the controller to take some action. And if that had to go through a cloud server that could be thousands of miles away, we could be talking 100 milliseconds of latency. And that's too long. The other paradigm that was used before fog computing, I should say, I'm sorry, is, or was, and still is, edge computing. And the example there would be a PC. You all know what it's like to have a PC running an application that's sending some data to the cloud every now and then, but most of the computing's going on in your PC. That's edge computing. And that still can work very well for some applications. But there are problems. For example, if two edge devices have to speak to each other. If we're talking about very simple edge devices, like a coffee maker, and it needs to perform a complex calculation, we don't want to put high-end processors in edge devices. When the edge devices need to speak to each other, how does a coffee maker find your coffee grinder? So a new paradigm was needed. And that's where fog computing comes in. And the idea is that you can put the fog platform very close to the edge. In the ideal case, it would be one hop away, but often it's a little further than that. And these fog nodes, or nodes within the fog platform, are doing computing. They can cache data. They can aggregate data for sending back to the cloud platform. They can summarize data and send it back to the cloud platform. And all of these things take load off the cloud, and they provide a very low latency solution for the edge nodes. And that's kind of the overview of what fog computing's about. Now, we have to look at security, which is a big issue for fog computing. And we have some comparisons on how fog computing versus cloud computing works. And I'll hand that over to Javan.
Sorry for the brief interruption, technical difficulties. However, I'll be discussing, my name is Jevin, I'll be discussing this connection of security and fog computing. Before that, we'll be processing and discussing the differences between fog and cloud computing. Could you go to the next slide, please? So I'll hand over to Schmidt, who will discuss the differences between cloud and fog.
Thanks, John. So just looking at the differences between fog and cloud, you could see that in terms of latency, fog computing has a very low latency, whereas the cloud has a very high latency. In terms of the distance, because the cloud is sitting so up high, there are multiple hops to the edges that needs to be taken, whereas with fog, it could be reached within a hop or two. As for the security, cloud security has been very undefined, whereas in fog, it's very definable, and Jawan will get into further details in terms of the security for it. And in terms of the mobility support, cloud has a very limited mobility, whereas for fog, it's supported and it's very scalable as well.
Thank you.
I'll just hand it over to Joanne to talk to more details about the security of fog.
Thank you, Schmidt. So security at a glance in the fog. So here the database represents the edge devices. So those devices are essentially susceptible, actually, let me rephrase that. The database refers to the cloud, which is only usually susceptible to data breaches and data loss. The striped cloud in the middle is the fog, which is subject to insecure application programming interfaces, system automation vulnerabilities, malicious intruders, such as man-in-the-middle attacks, insufficient due diligence, meaning not keeping up with patches, updates, changing policies, and so forth, abuse, nefarious use, as it states, and shared technology as data at the fog. It can be dispersed as a node. I will go further into the complications as it relates to that in a second. So edge devices, advanced persistent threats, like constant things such as DDoSs are examples of bad threats that emerge every day. Access control, people lose their passwords. People have silly passwords. People use password as their password. So those are just examples of that. Denial of service, which I previously mentioned, is constant forced connections to it, and which forces connection to interrupt or disconnect. Moving forward, so these are just some of the issues prevalent in cloud, or should I say fog computing. Cloud and fog are related to each other in extent, as with edge, so a lot of the issues overlap that can affect the fog. One I will discuss is virtualization, which is virtual machines, as it suggests, which are susceptible to attacks from many vectors. Uh, such as weak or no logical segregation, which it ties to the nodes fog computing once again. So possible solution for that is multi-factor authentication, which is having two forms of authentication. So for instance, if I log into my email on my phone, it will send another notification to the Mac that I'm using for me to provide a password in order to use that. That's an example. But so just pause for a moment here. You can review the slides if necessary if you want to, but I'll be moving forward. So this is just a quick man-in-the-middle attack. So the phone representing the edge device, the gateway would be the cloud, the attacker is at the bottom. The gateway being the fog in this case. The attacker would attack the fog, be in between them, the fog being the intermediate point between the cloud and the edge device. The person in the middle getting and sending information to the fog can just pretend they are the fog and capture information and not send it to the end device, or send it onto the end device as if nothing happened, but in fact they have modified or maliciously conducted something. Moving forward. So these are some of the pros and cons of cloud computing, fog computing, cloud, fog, mist. They're all paradigms that are going to be emerging, just as a fun fact to connect all three or four cloud security paradigms. So it's more scalable without affecting the cloud. You can scale the fog and add nodes to it without affecting the cloud, because the single cloud server you may have can connect to many fogs. It's a one-to-many relationship. There's low latency service to the edge devices, as previously mentioned by Schmidt. It's usually reachable in one hop, so there's not really time for jittering or really latency in between there. Smart allocation of resources. If you're strained for resources, you can add another fog node. If you're not strained for resources, you can remove the fog node. So it's intelligently spaced out. Moving forward, some of the cons related to fog computing are the deployment of numerous fog nodes. Security can be easily compromised if one node is compromised. So this is what I was discussing about the man-in-the-middle attack, or the other ones such as poor segmentation when I was discussing virtualization. Means many compromised nodes must get hacked. So henceforth, it has some security concerns there. There are relatively potential high maintenance costs. As you add more nodes, you add more costs. More with anything in life, more resource, more cost. Untested issues and theories due to it being a developing or emerging technology. There's not really too much established in the fog world. It has the standard was just issued by IEEE last year, so it's an emerging technology. Moving forward, I will be passing over to Rudy, who will discuss some of the applications of fog computing in the real world.
Hi, I'm Rudy. As noted by my colleagues, one of the key and strengths of fog computing is its ability to be scalable, have low latency, and efficiently compute given demand. And I'm going to use the example of law enforcement here to drive the point home. How often is a gunshot heard and people are unaware of either the source or what factors might have caused that sound? A fog environment would be able to not only detect whether it was actually a gunshot or not, but also be able to distribute the proper incident responding resources based on the interaction between the different nodes and clients and centralized computing that would happen. So, for example, given a gunshot and the sound wave it produces, you could imagine edge clients that act as sensors that can sort of decompose the frequencies and volume of the sound wave. If there's a fog platform that detects frequencies that might correspond to a gunshot, they can send it to a centralized computing database and compare it to known signatures of gunshot frequencies. That if it detects a possible candidate, that centralized computing resource can then dispatch first responders to potentially respond to an incident. All this happens in a matter of microseconds without any human interaction. So ultimately, fog environment would be able to greatly and with greater accuracy detect whether something like a gunshot or some other incident might have occurred and automate the response without the need of any human operator or without the need of overloading different sensors with the databases and the signatures, where each device can just sort of perform one computation really efficiently and pass on its data to other devices that can handle it in a better form.
To quickly add to Rudy's point, this technology isn't a new day. It emerged in 2015. It's called, its application is called the Spottrotter. It's used by police forces in New York City, Chicago, and Denver. As you said, a shot is fired. It sends up to a sensor, which is connected to the fog network, which connects to the central dispatch in New York City and dispatches it. So if people want more information regarding that, please feel free to check out Spottrotter.
Yeah, thank you, Javon.
Yep. Okay, well, thank you, everyone. And if you have any questions, please feel free to post them online.